So today we are going to talk about quantum variational circuits, and I will explain how quantum variational circuits are essentially just linear models in a different feature space or in a different vector space, usually a higher dimensional vector space, but you can have it a lower dimensional space as well. So we will talk about quantum variational circuits as essentially linear models, and then I'll explain how we can use them for classification problems, because in the same way you can use them for regression as well. And then at the end, I will show the implementation of QVC in for a couple of data sets, just to give you an idea how we can use quantum variational circuits for classification type of problems. So let me start by sharing my notebook. Okay, so let's begin. I hope the notebook is visible, and if there's any issue, Gibran, please let me know. All right. So we are going to talk about quantum variational circuits, and we can use this uh, QVC both for classification. Please pardon my spellings, and for regression problems. And what I'm going to show today is that they're essentially linear models in a different vector space, in a different feature space than the actual data space. And usually that is a higher dimensional feature space. Okay, but before I do that, let me take a little bit of a digression and go to classical linear models. So let me describe them for both problems. So suppose I have a classical regression problem. There's one feature and one output. Suppose the data is something like this. It's like looking like a parabolic curve. And we want to find a model that fit this data. And suppose we only want to do a linear fit. Then we can easily see that whatever we do, it's going to be something like this. It's not going to fit the data very well. However, if before I fit my linear model, what I do a feature engineering, and suppose I prepare another set of features. Let me call that feature map actually some phi of x. We can call it feature transformation, or just a feature map, or sometimes it's called feature engineering. And suppose what we do, we implement the feature map as x prime is equal to x squared. And in this case, suppose we get something like this. So our x prime versus y versus x prime could be something like this. Okay. And now I can fit a new linear model. Y is equal to some f theta in X prime domain as something like theta dot X, and the model fits pretty well. So this transformation made us fit our linear model better. So in effect, what we were able to do was implement essentially this model. Not f of x, but phi of x. So instead of implementing this one, we implemented theta dot phi x. In this case, we have the same dimensional space. We go from x to x prime, but sometime we can go to a higher dimensional or a different dimensional space as well. So similarly, and just by the way, this I can also write like some I1 to n as theta I phi I of x. Okay. Just like I theta I x prime. So this is my model is still linear, though it's linear in another space, not in the actual feature space. So it's a transformed space. Similarly, we can talk about another problem. Let's say I have a classification problem now, and suppose I have data points like this, like this. There are two features x1, x2, and there are some data points that are labeled, let's say, -1, and there are some data points that are labeled +1. And suppose again that I don't have the ability to implement a nonlinear separation boundary that can divide this set into two parts, where one part is -1, other part is +1. And all I can do is make a linear separator. So what I do that if I only have this linear separator, I can implement again a feature transformation. Suppose I can have an x prime, which is something like this, x1, x2, x1 square, x2 square. So this is my feature map. And I go to a new feature space with x1 prime, x2 prime, and x3 prime, where x1 prime is just x1, x2 prime is just x2, and x3 prime is x1 square plus x2 square. And we see that these circular data points, they are near the origin. So when I take the square, the third coordinate is going to be smaller for these points. So they're going to be lifted off of x1, x2 plane, but they would still be close to the origin. And these points with crosses, they have x1, x2 large. So when I take their square and add, I'm going to get the third coordinate very big. So these points might form a circle somewhere over here. And now I can easily draw a hyperplane that can separate the data into two categories. So again, my model is linear because I'm now using, instead of using this uh, plane in this 2D geometry, I'm using a plane in the transformed feature space like this. So which is sum over I theta I phi I. So it means this feature transformation results in a problem that we can linearly separate. Of course, in general, we don't actually know what feature transformation to use. That's actually the biggest design choice that an engineer has to make. That say if it's a high dimensional data, it's all mixed up. You don't know what phi fx to use. So what you do, you generally come up with a feature map that is parameterized itself. You know, the the feature map is again also parameterized, and in the process of implementing uh, this linear separator, we also try to find these parameters of the transformation map. Okay, so any question on the linear maps in classical machine learning? The linear transformation actually is very desired in machine learning problem. The reason is this, that it gives rise to a very simple cost function that we can write like this. Like these are actual labels, and let's say there are m examples, so I want to m. And since this predicted model is linear, what we get a paraboloidal type of cost function with with the a global minima only, and there are no local minimas. So it's a very nice optimization problem. So that's why this linear model is preferred whenever we can use. So instead of thinking of implementing a nonlinear model, what we do, we implement a feature transformation and try to keep the model linear. Just one uh, point that might come to mind, that we can also think of, let's say, transforming the parameters, and maybe in general we can think of transforming x as well. But this transformation doesn't give us any benefit, because we can just call the new parameters some theta prime, and then it is still, a linear model. And all we have to do now, instead of learning theta, we are just learning theta I directly. And since at the end, we don't, we can just use this theta I in the model. So this transformation is sort of a trivial thing. So whether you write it like this or you like this, it's still a linear model. And it's linear in the parameters. Okay, so the linearity is with respect to the parameters. All right, any question? If not, let's now move on to the quantum variational circuit, and specifically I'll talk about a variational quantum classifier. Sometimes it's written quantum variational classifier, QVC, sometimes it's written VQC, both names are used. Okay, and but whatever we say about this, in general, it's also applicable to our variational quantum regressor as well. So let's recall from our first lecture that we have a variational circuit like this. There is a data encoding block, and there is a parametric block, and then we find the expectation value of some observable. Let me call, let's take it to some a z tensor n observable. And then what we do, so this takes our data, and this takes the weight parameters. And just as a sort of a vocabulary, sometimes this data, we call this data also parameters, but to differentiate from weight parameters, these are input parameters. Okay, so we have input parameters and we have trainable weight parameters. And then once we have encoding and unsort, so usually this is called a feature map, and this is many times called an unsort, or sometime we call this a quantum neural network, and sometimes actually we use the quantum neural network term for all of this. So you can also call this variational quantum classifier as a quantum neural network, even though it's not exactly like a classical neural network, but it has some resemblance that we have a network with trainable parameters. So at the end, we can choose a general observable z, but I'm just going to show that we even if this observable whose expectation value we are going to compute, even if it is z, that can be general enough, provided that we have uh, a very good trainable circuit. And once we have a particular Hamiltonian, we need to compute the expectation of this observable age. And then based on this expectation value, we can have some interpretation that when to assign a label. So let's say if there are only two labels, we can take this expectation value and say, okay, if it's greater than zero, let's call the label as 1, and if it is negative, let's call the label as -1, and maybe we can use some other threshold instead of 0 as well. So these are the steps. Like we have a data encoding, a trainable circuit with weight parameters, and then we select a Hamiltonian whose expectation value we are going to measure at the end. And then based on the expectation value, we can decide the labels. And to update the parameters, we have to define a cost function. So the parameters have to be updated to, let's say, minimize some cost function that's that depends on x and theta, so that we are correctly able to identify the labels. Okay, so before we go into the implementation detail, let's just analyze this setup and see what type of model it represents. If we select the observable as a string of z operators. Sometime we also write it as sigma z. This is the poly sigma z operator. So this tensor n essentially mean we have sigma z, sigma z. So on each qubit, I may be acting with this. And really speaking, it doesn't even matter if we have sigma z on all of them. Even if we apply sigma z on one qubit and don't measure other qubits at all, even then we can train a circuit to predict the labels correctly. The reason is this, that all of these, this measurement, for example, this can be thought of as a measurement of a single qubit preceded by a unitary operator. So this, and we can find out this unitary. For example, if this is just ZZ, this unitary is just a ZZ feature map that we were talking yesterday. So it doesn't even have to be on each qubit. But anyway, for right now, it doesn't actually matter. So if this is the observable, then the expectation value of this observable is essentially, to start from 0, we apply Sx, and then we apply the parameterized circuit, and then we have our Hamiltonian Zn, and on the other side, this would become this. So this expectation value is just this because this is the state psi of x theta at the output. So the state here is psi x theta, and it's the expectation value of h is nothing but psi h. And this side is just the dagger of this stage. All right, now let's define a new observable, which we can write like this. So this is another Hermitian operator. It has to be because this is Hermitian. These are unitary. So this H is Hermitian, which means that I can write my f theta of x as, and let's write this s of x on 0 as some phi of x, h theta phi of x. So now if we look at this part, so this means that our variational circuit has been just reduced to a data encoding part and a measurement part, where instead of measuring the z operator, we are just measuring this new observable h theta. And when we are going to train this circuit and find the parameter theta that gives us a model that best fits our data or classify our data, it means what we are essentially doing is trying to find a measurement scheme that give us the model that fits our data, provided that we have chosen this encoding scheme. So varying theta is essentially equivalent to finding a measurement operator that gives us that when we measure it, it gives us a model that that classify our data in the best possible way. So when you change theta, you can just imagine that we are trying to find a measurement operator that will, when it's measured, it will give us, it will fit our data very well. And then this SFX is just the feature transformation. So before I do the algebra, you can now imagine what's going on. This SFX is essentially that it's taking us our data in a feature space X and transforming it to another feature space S1, S2, S3, and actually we have called it phi. So let me call it phi. So phi 1, phi 2, phi 3, and so on. So the data is going here. And then this h theta is essentially giving us that, a separator of the data. And it's like when we are varying theta, we are trying to find this hyperplane that is separating them. Or equivalently, you can think of in from the measurement perspective that this transform the data into higher dimensional space, and h theta is then we are just trying to find the best measurement scheme to predict our labels in the best possible way. And we can see that it's a linear model if we think of this thing, that all Hermitian operators, they can actually be written as sums of Pauli operators. Okay, so for example, if this H is a 3-qubit operator, so if H is this 3 qubit, we might have some term that is sigma z, sigma z, sigma z. We might have some term C1 identity. We might have some term C2 identity, tensor X, and so on. So there are essentially 4 power 3 possible terms in here. So this is like one polystring. This is another polystring. This is another polystring. So that's what alpha mean here. And this C alpha, which is a function of theta, it actually depends on this parameter theta and this whatever this Hamiltonian is. So since we can write every Hamiltonian, every observable as sum of Pauli operators or Pauli strings, I can transform my model like this. So this F theta, which we had just written like this. If now I substitute that view, so it becomes C alpha phi x, P alpha phi x. Okay, and now let's look into what this is. This, let's call it uh, some phi alpha that depends on x, and actually instead of using capital phi, let me use a small phi just to make it different from this phi. So that's a different phi, this is a different phi, and this is this. So our model becomes C alpha dependent on theta, and then phi alpha dependent on x. And if you look closely, this is nothing but a linear transformation in the transformed feature space. So I can expand it and write it like this: C1 of theta phi 1 of x plus C2 of theta phi 2 of x, and so on. So where these C1, C2, etc., these are the trainable parameters that we are going to vary in the model. And this phi 1, phi 2, etc., this is our new features. So let's call it some x1 prime. So C2, x2 prime, C3, x3 prime, and so on. So this F theta is just a linear model in the feature space. Any question so far? No? Okay, perfect. Now let's now go to the training of the variational quantum classifier or any variational circuit. So in the variational circuit, again, just to recall, we have a setup like this. Some observable where we just chose the observable to be z, and the unitary is some W of theta S of x. And actually, this can be even more than that. We can have the mixture of this theta and x part, where we are repeating in different layers. So in this case, the this f theta, what one group did is that to understand the behavior of the circuit for training, what they did, they had a very deep uh, circuit, and and it had like randomly distributed unitaries, to put it simply, and they worked out its derivative and the variance of the derivative, and they found that the derivative with respect to these parameters, they're near zero. And not only that, the variance of these derivatives was also scaling as 1 over 2 power n. So where n is the number of qubits. So if you have like n 100, you can imagine that this variance is almost zero, and even at n 10, this variance is close to zero. I mean, not only that the derivative is zero, this derivative is not even changing uh, for a very large part of the parameter space. So these are called barren plateaus. And these circuits suffer from this thing, that if we have a very deep circuit, in general, maybe not always, but in general, you can expect that their training would be slow. However, it was also found that if the circuit is not deep, then it doesn't suffer from this barren plateau. And not deep mean the circuit is shallow, and shallow means that the depth are the number of layers. They are sort of less than the order of the square root of the qubits. Like if you have 100 qubits and your circuit has about 10 layers or maybe less, then it wouldn't suffer from this training pit. So that's one key thing that we have to keep in mind when we are training our variational quantum circuits, that try not to go for very deep circuits. Any questions before we implement it in a code? There's a question, could not get the concept of barren plateau for deep and shallow circuits. So let me try to explain it again. So if the circuit is deep, deep circuit mean that the number of gate layers, they are much larger than the number of qubits. So let's say if there are 10 qubits and you have 100 gate layers, so that means the circuit is deep. And not always, but in general, you can expect that the derivative with respect to the parameter would be zero. And since derivative is needed, for example, in a gradient descent type of routine where we update the parameters based on some learning rate, and the derivative of the cost function with respect to the parameter. So if this is close to zero, it means that the new value of parameter would almost be the same as the parameter in the previous iteration. Because when we are training in machine learning algorithms, we try to get better estimate of parameters after each iteration. And if this derivative is zero, it means that in each iteration, we are not able to get better values of parameters. And this is called barren plateau because if you plot, your cost function or maybe the expectation value as function of some theta, it instead of looking like this, it looks something like this. That if you start here, you can't go this way or this way. If it had looked like this, that you start here, you can keep going down and you can minimize. So this is what we call a barren plateau. And we can avoid this barren plateau if the circuit is not deep. It's a shallow circuit, which means that its depth should be less than of the order of the square root of the number of qubits. The why derivative is zero, it's a big question. So you can just Google the barren plateau paper because the derivative was computed for a host of circuits that are uniformly randomly distributed, and from there the derivatives were estimated. Because to actually show that the derivative is zero, you have to find the function of theta of x and then find its derivative. So that's seems like a usual way, but that mean that what you will do will only be true for a specific circuit. What they did, they said, okay, let's take a circuit that has randomly distributed unitaries, so that can represent any sort of typical circuit on the average, and try to find its its expectation value and its derivative. All right. So let's now see the steps to implement this in a code. How to implement in Qiskit. So what you need to do, you need to start from your data set, create or have some data set imported into your file, and remember to scale the data. Okay. And in my notebooks, it might not be scaled, and you will have to scale it yourself. And then, and if even if you work without scaling, it will still work, but the results would not be that good. If you scale, the results could be pretty good. Okay, and once you have a data set, then you choose a feature map to encode your data X, and then you choose uh, a parameterized circuit. And by the way, you can have the same circuit as a parametric circuit and as a feature map. There's nothing that bars it. And then you run some minimization routine. Uh, and actually, before minimization, you have to do one other thing. Sorry about it. Okay. So what you have to do is you have to select a cost function. And even though for classification problem, there are cost function like binary cross entropy, etc. that works better. I have chosen a simple mean square error function for the problems that I'm going to show. And I also checked with binary cross entropy, it almost works the same. And then you run a minimization algorithm to minimize this cost function, and you get the trained weights. And then once you have these optimal parameters, you can use it to do the prediction on a data set. Usually, when we have data set, we divide it into training set and the test set. So we train on a training set and we use the test set for the prediction of the results. Okay, so let's go over to the codes and download the two notebooks from GitHub, and we will. So, what about the scale, the data set? Any data set it's suitable, or is there any decision about that your what data set are not suitable? All data sets are suitable. All you have to do is just scale. For example, your features are like this minus 7 to 0.1, 10, 11. No, it's better to scale it if you want to use it for angle encoding or phase encoding, etc., which we usually do, to so that each is a value between 0 to 2 pi. And that will make sure that different points are encoded to different states in the quantum circuit. So all data sets are suitable, but before we use the data, we have to do this scaling of the data, rescaling. And I'm actually going to show the impact of scaling in the files today. So the difference between training set is this, that it's the set that we use while we are running the minimization algorithm, and we don't use the examples from the test set. So let's say we have 100 data points. So we reserve, let's say 10 or 15 or 20 points separate and just use the 80 points to train the algorithm. And then the rest of the points, which we already know their label, we then feed them to the algorithm to see if it predicts their label correctly or not. If it doesn't predict the label correctly, it means, that's an error. So that's why it's called a test set. Okay, so let's download the files, and let me also set up, and we can meet in 4 minutes to implement it.